Hi, this is Ming Yao from Singularity Engineering. This is our part 4 of our video series on ventilation simulation. In the previous parts, we've gone through how to clean up a rivet model, set up a basic air change per hour or age of air simulation, and also looking at how to characterize the diffuser. In this example, we're going to add temperature and natural convection to our analysis, and we will include accurate diffuser models as well as accurate wall boundary condition models. So hopefully you enjoy this video. And so we're using here we're going to start out with a mesh that we've already set up. I've simplified the desks a little bit so that the mesh count is low. Okay, we have our model here. This is our classroom model. You can see I've changed the supply to little square boxes, and I've put a return over here and a return over here. So kind of spread out the return and the supply, made them on opposite sides of the room. And now let's go ahead and set up our simulation. So much of this will be the same. We're going to use air at 25 degrees Celsius. We're going to make this buoyant, and I'm going to put in a directional acceleration to turn on the buoyancy effects, and the reference temperature is let's say 25 degrees Celsius. Turn off thermal energy so that we have heat transfer calculated, and I'm going to switch to a shear stress transport turbulence model. We're going to turn off thermal radiation for now. There's nothing super hot in this environment. If we want to shine some light through these windows and look at how that affects the room temperature at different parts of the day, we can do that, but for thermal analysis, we're going to keep it simple. Meters per second squared. So it warned me of an incorrect unit there. So that's it for that part of it. So now we want to put in the inlets and the outlets. So the outlet part is simple. So we would set that to be called return. And this will be an outlet, which will be here and here. We'll have average static pressure of 0. And for the inlets, or the supply, I think we had a temperature, put the supply temperature as a parameter. So we can specify some parameters for flow rates and things. So let's go ahead and start specifying that. So this will be supply temperature, and this is actually an equation. So I'll talk about this equation a little bit. So here we're going to add up the temperatures at the return. So we have the mass flow average temperature at the return 1 plus mass flow average of the temperature at the return 2, and we should add all this together and maybe add 25 degrees Celsius to it. So this means that whatever temperature we get at the return, the air that comes through the inlet will be heated up by an additional 25 degrees Celsius. And we make a maximum number just in case this number is incorrect. It can be the lowest temperature that comes out of the supply is 25 C. So we can make some adjustment to this if needed. Then we need to put in a flow rate. So this will be my supply flow rate. And here I'm gonna say it'll be 5. So there's 2 supply ports here. They will be 500 cubic feet per second per minute times 1.185 kilogram per meter cubed. Okay. So this converts our volumetric flow rate to a mass flow rate. And there's 2 of these, so each will be dumping in 500 cubic feet per minute of air, which makes this up to 1,000 cubic feet per minute of air in total. And finally, we want to figure out what the angle of the diffuser flow is. So we're going to go back to our previous. I'm going to do a few things here. First, we will find our document on our diffusers. Okay, so here's the diffuser catalog. I'm going to go down here. We want a square metal type of diffuser. It's a foot size, 1 foot by 1 foot, and it's about 500 cubic feet per minute. So that'll be this one here. And we can see the throw is about 9, 11, and 15 feet. So we can go back to our previous diffuser calculation model. And I can say, let's go into here and we'll change our parameters. This one here. So we know our flow rate is 500, so 500. So it should be 8.3 here, and now we need to do some interpolation because it's 9, 11, and 15 here. So let me delete these 2. Or we can try a slightly different one, but let's try to use these. So 8, 10, and 14. So it should be a little bit higher than that. I'm going to seek a target for all of these. You can see on a smaller size it's 8, 10, and 14. So it should be 100. It should be higher than 150 feet per minute. So let's just do, let's say 160, 110, and 60. So add kind of 10 feet to each one of these. Just go ahead and do an update, and Ansys will kind of extract 5,000 potential designs from my data points and calculate a response surface for me, a candidate point for me. And it gives me 3 options. So it says you got everything from 50 to 47 to 45. And if we look at the parameters of interest at 8, 10, and 14 feet, we want something in this range. So so really we want the 8 feet here to be higher than 150. This to be higher than 110. This should be higher than 50 feet per minute. So maybe the first one looks like it could be the best, or maybe this one here, right? You have something that's about 70 feet per minute. It's the lowest one of the data we have here. So I'm going to go with this one, which is roughly around 50-degree angle. So not super exact, but this is a good estimate of what our flow angle is coming out of the diffusers based on our expression. So okay. Oh, I think it should be degree without the S. Evaluate it. Yeah, so it converts it to an angle. So that's good. So we have our diffuser angle, supply, flow rate, and temperature. And now we can put in our inlet. So I'm going to go do supply 1. Actually, before I do that, I should put in the coordinate systems. Right? We need each of these supplies to spread air along the top of the ceiling at a 50-degree angle. So let's go ahead and put in some coordinate systems. Coordinate 1 will be here, and coordinate 2 will be here. So we just need the z-axis to point upwards here, normal to the supply location, and then the rest should work out just fine. So now we can do supply 1. It's an inlet, which we'll select as that. Switch this to mass flow rate. Since we already have an expression, it's now easy. So this is our flow rate. This is our temperature. And here we're going to adjust the direction to be a cylindrical coordinate system. It's going to use coordinate 1 z-axis as the rotational axis, and this one is, I believe, minus sign. Let me double check on this. Oh, minus cos. So this is minus cos. Oh. So diffuser angle, and this is sine, and that's 0. So that's I had this as a different return, but I'll just put in the other supply first. Once again, the mass flow rate and expression I created. Static temperature, I'll fix that expression shortly. And then the flow direction will be based on coordinate 2, third axis here, and this will be minus cos angle. It's going to be sine and this is 0. Okay, so having trouble with this parameter because previously I separated out the two return as separate values, but here I lumped it together, which means we don't need to do this anymore. We can just have a single return. And usually it's not 25 C. Usually you want it to be about 20, actually Fahrenheit, be the difference between your supply and return temperature. Now in that case, this expression could cause thermal runaway. If I always have the temperature coming out here much hotter than this, then much hotter than the return temperature, it's possible that the temperature will just keep increasing and increasing. So we want to put this should be actually a minimum value, and it'll be the minimum of either 30 degrees or this temperature. So we'll see at what temperature the supply ends up being. But looks like I have one too many brackets here. Okay. So now we have 2 supply and 2 returns, and now we want to set in some other boundary conditions here. So we want to put in, assuming we're heating this up in a cold environment, we would have fairly cold outside temperatures. Let's pretend this is California. Maybe it gets to as cold as 0 degrees Celsius or freezing. So we're going to assign windows, and these will be walls. That's these windows here. Okay. And it's gonna have a heat transfer coefficient to it. So windows and walls, you can always find the R values for them, and it's a pretty simple expression. If you know what R value is, and you have an estimate of what the outside heat transfer coefficient is. For example, on a windy day, we're gonna assume it's about 50 watts per meter squared. You end up for a single pane window of 5 watts per meter squared degrees Celsius. So we're going to set the outside temperature to 0 and the heat transfer coefficient here to 5. We may also have some walls that are exposed to the outside. For example, maybe this is a outside wall. So let's do a wall here. And again, we can put in the heat transfer coefficient of, so let's say this is a R13 wall, so then the heat transfer coefficient drops down to 0.432, and again, the outside temperature is 0 degrees Celsius, which is 32 Fahrenheit. So that's a temperature calculation that we've set up here. And we can also put in our old age of air calculation. So let's add age of air, and this is just in seconds. It's a volumetric in seconds, volumetric scalar. We want to turn on the age of air and have this be transported using all the transport equations. And then we want to put in a subdomain everywhere on this body, and we'll add a source of 1. So going back to the 2 inlets, we need to set these as 0 so that the air is going to come in at 0 seconds, and it'll take a while for it to leave the domain. So sometimes things like age of air will converge fairly slowly. So to monitor that, we definitely want to turn on some monitoring points. So there's a few ways to do this, but we want to go to output control, and we want to monitor basically the maximum age of air in the domain. So max age of air. Let's monitor this using the expression, and we can just type it in here. So I want the max value of age of air at default domain. Okay. And then we want maybe max temp. I want to see what the maximum temperature is here. So this will be, we can find a max value of variable, lots of variables here, but we just want the temperature at a location, default domain. Okay, so we're monitoring those two. We want to run the simulation for a while, so I'm gonna set this to 1,000. And that's it. 1,000 iterations. Let's go ahead and run our simulation now. Okay, I'm going to use 5 cores to run the simulation. And off we go. So you can see that we're monitoring the age of air in red here, maximum temperature holding steady at 85, 86 Fahrenheit. And then the additional variable convergence is coming down. We have heat transfer, turbulence, etc. So we'll let it run for a little while here. Okay, the simulation is converting fairly well after 400 iterations. We can see the user point though, the residence time of the air is still going up quite significantly, so we want to speed this up a little bit. In CFX, there's a nice tool that allows us to quickly change the settings. So we're going to speed up my simulation significantly since the flow has pretty much converged. So I'm going to change this time scale factor to 3, which allows us to increase the speed of convergence by 3, and we should see convergence speed up appropriately. Okay, the simulation is completed. You can see that the momentum terms converge pretty well. We're shooting for a 10 to the minus 4 drop, and we've certainly reached that here. Heat transfer just reached that as well. The additional variable terms are a little bit bumpy, so this is the term for the age of air. You can see there's still some variations here, but in terms of reaching a maximum, it looks like we've hit the peak, and maybe this will drop down and fluctuate a little bit. So to get really accurate answers, we probably want to continue the simulation for a while, but the results are pretty good as it is. We'll assume that we've ran this for another a few hundred iterations to get a converged result. Now we can go ahead and see what the result looks like. Okay, so let's take a look at the streamlines first. We're going to start from our 2 supply locations. And you can see that it's following our 50-degree flow downwards. I think a lot of the folks in the ventilation industry calls this the Coanda effect, where the flow hugs the wall. And you can see it's capturing that very nicely. It's coming down and eventually being sucked up by the return here and the return here. We can take a look at the planes. So this shows you the age of air at, I believe this was at about 1 meter. Let's do 1 meter. Okay, and 600 seconds about here, so about 10 minutes in these areas, in the reddest area. So we're getting ACH of about 10. The flow hugs the wall, so we can see the flow kind of clearing out a lot of the areas near the wall very quickly. We can also take a look at the temperature on this plane. Here we go. Okay, so this is in Celsius. We can certainly switch it to Fahrenheit. So it's pretty warm. Looks like local temperature is about 30 degrees Celsius. So certainly more than warm enough to heat the room. We have some cool areas here near the windows. We can make this a little bit taller because I think the let's do 1.5 meters. So near the walls, we're getting down to about 8. Near the windows, single pane windows, it's 8 degrees. We can certainly switch that to double pane windows and see what the results are. We can also do a lot of different calculations. For example, we can do maybe an area integral at the window of the heat flux. Okay, so it tells us through the windows we're losing 375 watts of energy, which is not too bad actually. And then we can do the same thing for the wall. Right, 200 watts of energy. So it's a well insulated room. In real models, you may want to specify the top and the bottom too, if there's heat loss through the roof or the floor, depending on which floor this is on, and also some of the other walls. But as long as you have good R values, all of this information should be fine. Yeah, so you can see that in this one simulation now, I should also plot a temperature plot like this. You can see that there's a hot temperature from the supply on top, but there's also a certain amount of natural convection. So cool air tends to drop to the bottom, hot air rises to the top, but we also have hot air feeding into the classroom, and then there's the returns on the bottom. So depending on where the return and supply is, we can have different types of results. So this is a quick example to show you how putting all the things we've done together. Now we included temperature, so we can predict the heat performance of the room. We can put in realistic diffusers, realistic boundary conditions for our windows and walls, and natural convection, and the rest of it all simulated. So a quick example of setting up these simulations. Hopefully you enjoyed this video. If you like the videos, please click on the like button, and certainly please subscribe to our channel. Have a good day. Bye-bye.